Hello again. This is Math 1120 coming to you from the College page, and the title of this lecture is Applications of Newton's Laws. And I encourage you to be an active learner while watching this video. Let's begin by talking about what it means for a particle to be at equilibrium. When an object is at equilibrium, or in equilibrium, the vector sum of the forces acting on it must be zero. So that's the summation of all the forces are zero. And in component form, that means that the summation of all the forces in the x directions must be zero, and the summation of all the forces in the y direction must be zero. Now, as we discussed previously, free body diagrams are useful in identifying the forces that act on an object being considered. And Newton's third law is also frequently needed in equilibrium problems. So, the two forces in an action-reaction pair, that is Newton's third law, never act on the same object. So let's consider then an object on an inclined plane. And so this inclined plane is going up at an angle of alpha, and we've got a box on this inclined plane. Well, there are several things that are going on. One thing that is going on is there is the weight of the object, which is going towards the center of the Earth. But we also know that that weight of the object has x and y components. It has an x component, or a component parallel to the surface of the inclined plane, not an x necessarily. I guess we're calling it x here, though, which is going to be the weight times the sine of alpha. And there's going to be something that is going down like this, which is a force normal to the plane. Now we talk about the normal force going up here, but since this isn't moving, it's staying on the surface, then what you have is this perpendicular going down is W cosine alpha. That's the component of the weight that is pushing down. And then we have a component of a force that is the normal force that is pushing up, and those are of course in balance. And so the summation of those y forces is zero because they're in balance. And the summation of the x-ray forces are in balance also if it is in equilibrium. So this is a free body diagram, and we see the weight vector is replaced by its components. Let's do a problem relative to this. So we're going to apply the problem-solving strategy outlined to obtain a simple one-dimensional equilibrium problem. So we have a gymnast hanging from the lower end of a rope connected to an O-ring. There's the O-ring up there that is bolted to the ceiling. The weight of the gymnast, the rope, and the O-ring are 500 newtons. That's how much the gymnast weighs. 100 newtons, that's how much the rope weighs, and the O-ring is 50 newtons. Those are respectively. So what are the magnitudes of the tension at both ends of the rope? And you see there are tensions at both ends of the rope. So we will draw a picture. There's a broad picture, but let's now do a diagram talking about what's really happening. So here's the gymnast. The weight of the gymnast is 500 newtons, okay? And then the rope has to be balancing that because the gymnast is hanging there. It is in equilibrium, and so that is going to be T1. And so T1 is there, and T1 is there. Now above that, though, what happens is, and this is on the O-ring, not only is the weight of the O-ring there, but also the weight of the rope and the weight of the gymnast. And so we have a T2. And so T2 is the tension here, but it's balanced, and it's also T2 is down here. And so, you know, that's what we have. Those are the pairs. So what we're going to do then to solve this problem is consider that picture. And we're going to say that the gymnast is motionless. So we know that she is in equilibrium. Since we know her weight, we can say the summation of the forces in the y direction is equal to 0, and we can find the magnitude of the upward tension, T1, on her. And so the summation in the y direction is 0. So that is T1 plus, but then this is 500 newtons going downward. And since we're in equilibrium, this sum of the forces has to equal 0. So T1 is equal to, we solve that, that is 500 newtons. So the two forces acting on the gymnast are not an action-reaction pair because they're not acting on the same object. Next, we need to consider the forces acting on the rope. So Newton's third law tells us that the gymnast exerts a force on the rope that is equal and opposite to the force it exerts on her. In other words, she pulls down on the rope with a force whose magnitude T1 is 500 newtons. As you probably expect, the force equals the gymnast's weight. But the other forces on the rope are its own weight, 100 newtons, and the upward force, magnitude T1, exerted on the upper end by the O-ring. And so when we say that those have to equal 0, the summation in the y directions are, this is T2 minus 100, and then it is also minus 500, which we found from up here, and that's equal to 0. That means that T2 is equal to 600 newtons. So that's a good example for us to do about the equilibriums. Now, when we're having ropes or different kinds of materials holding things up, there are breaking strengths of these. If you have a thin white string, that can be broken reasonably easily with a 50 Newton force. If it is a nylon clothesline rope, it is much stronger. In fact, in this case, it is 80 times stronger. If you're climbing mountains, and depending on the diameter of the ropes and the materials of the ropes, it's much stronger because you don't want to fall off a mountain. And if you're lifting things, you can talk about having steel cables, and those are even much stronger. Let's move on now, and now we're going to talk about not only one-dimensional, but we're going to talk about two-dimensional problems then. Okay, so now we're going to look at an example. There's several forces acting on an object, but in this case the forces are not along the same axis. So we have a picture here, and you see what we're doing is we're lifting an engine up, and we're lifting it here, but it's also anchored to the ceiling, and there's an angle of 60 degrees that is there. So what we're saying is, if this is in equilibrium then, so what happens is that there is an up and sideways force happening across with this T2 because it's pulling up and over, and this one is just pulling over, and this one is pulling up. So we have to balance all of those. And here's the free diagram that we're really looking at. So T3 is at an angle of 60 degrees. And so if we resolve T3 into its x and y components, we get T3 times sine of 60 and T3 times cosine of 60. So that's telling us what are those components. And again, we can replace the T3 by its components. And then we got T2 going this way, and we have T1 going down. Okay, so we're going to apply the equilibrium conditions because the problem told us we were in equilibrium for the ring. And so we're going to write separate equations for the x and y components. So the summation of the x components tells me that T3 cosine 60 minus T2 has to be equal to 0. Because T2 is going this way, T3 cosine 60 is going this way, they have to balance each other to be in equilibrium. Similarly, in the y direction, T3 sine 60 and minus this have to be the same. Again, they're vectors, so we have to be concerned about the SIGNs. Okay, so we have two equations and two unknowns to solve. And but we can say, okay, but T1 is equal to W, so we can rewrite the second equation just using W there, and so we have T3 is equal to, that is going to be T1 over sine 60 when we solve for that, and that's W over this, and we know that W was given in the problem somewhere the weight was given, and so that, or excuse me, I guess the weight is not given yet. The weight is given later. The weight is 2200 newtons. That's 500 pounds. So that's given down here. So anyway, we have 1 over the sine of 60 is 1.115 W. Now that tells us what T3 is. So we can substitute that for T3 into the other equation. And so we have that T2 minus T3 cosine theta is equal to that, or excuse me, we have T2 rather is equal to this, because we already had that definition. So T2 is equal to T3 cosine theta, and so that's this times the cosine, so that is this in terms of W. Now, if we know what W is, it's 2200, then the solutions are going to be, we plug this in, and we find that T1 is 2200 newtons, T2 is, we're putting the same value in for W, and T3 is the same value for W, and so we solve for all three of those. Now here's a place for us to test our understanding of this first section in this chapter 5. So if you push a box across a horizontal floor with a force W alpha, and so here you're pushing it, and actually that's WA, that's a force WA, that is angled below the horizontal, and you see they're saying below the horizontal because if it was horizontal it would be like this, so there's an angle below the horizontal. How does the magnitude of the normal force from the floor compare? Normal force from the floor compared to the weight of the box as you push it. The normal force from the floor could be less than the box weight, it could be equal to the box weight, or it could be greater than the box weight. So you should think about that. Again, I don't give you multiple choice questions, but this is a good concept thing. And let's look at the solution. As the box slides horizontally across the floor, it doesn't move vertically. Therefore, the vertical component of acceleration must be 0. This means that the upward pointing normal force must cancel both the weight and the vertical component of this, because you see there is a vertical component of this, which points downward. You see this gets resolved into going over this way and then going down, so it is pointing down. Therefore, the correct answer is C. Notice it's not clear from the problem whether or not the horizontal component of the box is 0, but doesn't affect our answer for this problem since we're concerned only with what's going on vertically. Let's talk about what happens then in section 5.2. And this is applications of not the equilibrium, which we were talking about in 5.1, but Newton's second law. And Newton's second law, you recall, says that the net force is equal to the mass times the acceleration. And if we look at the components, the forces in the x direction are also responsible for the acceleration in the x direction, and the forces in the y direction are also responsible for the acceleration in the y direction, and F equals ma as we see. So if you're on the inclined plane then, and you are looking at a free body diagram over here, so we're saying, okay, you still got this box. Again, we have the weight, which has a component going down the inclined plane, and it has a component that is perpendicular to the inclined plane, and that's balanced by the normal force, because it's not going perpendicular. There's no acceleration happening there. But then you could be talking about, oh, but I want to push this up, and I want to push this up with an acceleration. And so you see going up here, what we would say is that for this to be the acceleration then, the force in the y directions is going to be 0, because this is going to balance this. But in the x direction, that is along the inclined plane, we're going to be looking at the comparison of the acceleration with the mass times of the box times this, and we're going to be comparing it with this. And the summation of these forces is going to tell us what's happening with the box. And it's going to be the net force is going to be the mass times the acceleration along, up, and down the box. Now we're going to do some examples of this when we return in the next video. But in closing, for now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.